And I was told that you should use macros the same as now. So the C was about coloring some points in two different colors. So you wanted to have. Okay, you can tell them. I'm not very good at talking about it.
So from C, we are given a simple undirected graph. So maybe something like this. And we are told that as you traverse this graph, when you come into some vertex, you have to wait some amount, right? If you enter vertex u, you have to wait t sub u. Okay. So you enter u, you have to wait. And we want to go from vertex 1 to vertex n in shortest path way. So if there's some way to wait 5 seconds, we want to only consider paths that take 5 seconds. And for any path, any optimal path, we want to make sure, okay, so we are asked to color this graph in 2 colors, such that for any optimal path, there is at least one edge that is painted a single color. And that might sound trivial because you just painted up the same color and you're done. But we're actually told to paint an exact number of vertices. So we're given some number k, and we have to paint k vertices of one color and n minus k the other color. Oh man, I forgot about the microphone. Okay, is this good? This is too far already. Is this good for the microphone or closer? Okay. Was that loud enough explanation? Okay, good.
I can try to say it again. So we have a weighted graph, but the weights are on nodes, and we want to find color, not color, but we want to color the nodes into 2 colors. We have the exact number of nodes we have to color in one color and the other one, and we want to make sure that the shortest path between the shortest path between 1 and n contain a monochromatic edge.
Yes.
Yes.
Okay. So first thing to notice is we can use Dagger's algorithm to find which edges are on optimal paths, right? So we can do Dagger's algorithm from vertex n. That's going to tell us for each node how long it takes to go from that node to n, right? Technically, how long it takes to go from n to that point, but this is bidirectional, so it's the same thing. And then we can use DFS from node 1 to discard any edge that is not optimal. The way we check if an edge is optimal, we're going to have some vertex u, some vertex v, and some weight w. And this edge will be optimal for going from u to v if the distance at u plus w equals the distance at v. So, you know, like as you do the extras, there's like this relaxation step. If this has the correct value, then it is optimal. It means that it was.
Why do you need a separate DFS to do that?
That's just how I implemented it. Yeah, I think you can just do a for loop, maybe. Yeah. What's neat about doing DFS is that you don't get anything extra. I mean, you can have this condition and also that the entire path is optimal. So it's a little bit easier, maybe. Well, after we do this, the shape of the graph will be very particular. We can direct the edges as we do this so that they get closer to n. and we will end up with a DAG that's directed from 1, going away from 1, going towards n, and there's only one root and one leaf, right? Because this is like the origin point, and this is the target point, and of course it doesn't make sense for there to be edges like this, so that's why there's only one leaf. And this is the only starting point, so of course there's not going to be any other starting points. So these graphs are kind of nice. It's not so important for the solution, but it's a nice thing to observe. Now suppose we take some topological order of this graph, this DAG. So for instance, let's say let's just number the nodes. And one possible topological order, I think, will be 1, 2, 3, 4, 5. That's one topological order. And we're just going to color k nodes, okay? The first k, we're just going to color them, and that just works. There's a few extra cases to work out, but in the general case, this is correct. And the reason why goes as follows. Consider any path from 1 to n that has length greater than 2. Okay, so we have a path that has length, 3 or more. We color like this, and this path is going to be like monotonic on the topological order, just like by definition of topological order. If there's a path, it has to be monotonic. And since we colored some prefix of the topological order, that means we have also colored some prefix of the path. Now note, if this prefix on the path is just one node, then this must be 2 or more nodes, right? Because we know this is at least 3, so if this is only 1, then this is 2 or more. And that must mean that here, there's some edges that we have not painted, and that's good. That's enough. On the other hand, consider the path, and consider the case where we have colored 2 or more at the start. And then, well, we don't know nothing about this, but that's okay, because if we have colored 2 or more at here, we're done. Like, this is a fully colored edge, and it's also a solution. So yeah, that's like the general case, and there's one really important case, which is when there's this edge, 1 to n. If you just do this, at least the way I code it, it's not going to work. I check this especially. And if you have something like this, if one is connected directly to n, and you only have k equals 1, this is not going to work. Because we try to color this one will be, so we have edge 1 to n. We say, oh, do topological order, I paint this one. This is not painted, this doesn't work. But that's because it doesn't have this property of path being 3 or longer. Now in this case, if n equals 2, and this is a whole graph, it's just impossible. But if there's some other node out here, we can say, well, don't paint this one, paint that one. And that works. And you have to see that you can leave 2 nodes unpainted. I guess it's n minus k at least 2, something like that. Yes. And that's it.
Okay, so in general, the only coordinate case is when we have the shortest path is between 1 and n, and the only thing when it is impossible when k is equal to 1, which it was even a sample test, so it was visible that is the only thing. If we have something that has more nodes, then there's always a way to color these in some way. So basically, you want to make sure that 1 and n has the same color, and that's the only thing that we need to care about. Questions?
There is a simple solution without dash or dash.
Okay, well, I want to hear it. I'm not aware of that. It might be like are there any other questions about this solution? Thank you very much.
Question? A question? Okay. Do you want me to erase it?
No. The only edge case is this one.
Uh-huh.
If there is no edge between 1 and n, consider like this. This is 1. This is n. This is the guys who are neighbor to both. This is the guys that are neighbor to only n, and this is the guys that are only neighbor to 1.
Okay.
We will color this like color this and not color this. It doesn't matter what we color here, because if we go here, we go straight to n. So either this edge or this edge will be good. And then the other vertices here. So now you have these two groups. If we color all of these vertices or not color all of these vertices, you're good, because when we go from here to here, it's okay, and when we go from here to here, it's okay. One of these two has size less than n over 2, so we can always do it.
Okay. I see. Yeah, that's pretty cool actually. And it's way easier to implement because you don't have to worry about the H service all the time. Awesome. Yeah, that is great. Any questions? Awesome. Thank you very much.
Do you want me to erase it?
Okay, we have 6 problems left. Any other volunteers to talk about any of these problems? Which one? And you? H and E. E will be later. I want to hear about H first.
Okay, so in problem H, they give you a bunch of, they say programmers, which we'll think of as points because they have 2 abilities. I think it's the speed at which they code and the speed at which they fix bugs. They give you a bunch of points. And then they ask you queries. They ask you a query about a point. They basically ask you if there's some combination of programmers which is better than this point. By combination, I mean convex combination. So you take, for example, A.
Maybe you can make a different one?
Yeah. So you take numbers A1, A2, A3, and so.
Maybe a little bit makes your font bigger.
Okay. You take numbers A1, A2, A3, and so on that sum up to 1, and then you do a combination of programmers with those coefficients. So like A1 times this programmer, A2 times this programmer, A3 times this programmer, and that gives you a point somewhere here. Combination of the 3. And that has to be better than this programmer, so it has to be like this, right? That's the query they ask you, if you can do that for this new point. Yeah, and the story is that
Maybe you skip the part, I just want to make sure that everyone knows. So we can represent these programmers as 2D points. One point is skill, and one coordinate is skill, and the second coordinate is time. And then if you think about the like the average, or like the what is the name of that?
convex combination.
Convex combination of these. So we are basically looking to find a point that is. Okay, I don't know. I think I will go a little bit ahead. So okay, so we represent these people just as 2D points, and then there's like a very interesting property about about these points. Okay.
that wasn't very helpful.
Okay. So yeah, the problem statement simplifies into that basically. We query a point and we ask if there's a convex combination of the other points which is better than this one. Okay. So you can, and there's also ways of taking out these programmers. They die. Okay. So first we can analyze the problem by drawing a bunch of points and seeing what the region where the query is true would be. So, for example, if we have a programmer, then this whole rectangle would be true, right? Because by just taking the trivial combination, that whole thing is true. And for all rectangles, for all programmers, we have that, right? But that's not the only region that is true. You also have these triangles here, okay? Because in those triangles, you can always take a combination of these two programmers. And yeah, that's always going to be better than the whole triangle, right? Is that clear? So what you end up with is like the convex hull of the points plus these two lines here, right? So you need to be able, like one approach would be to be able to keep the convex hull online, to be able to take points out, and doing queries to check if a point is inside the convex hull, but that's very hard. I don't know how to do that. So what you can do instead is reverse the queries and have queries of adding points to the convex hull, and then queries of checking whether a point is inside the convex hull, right? Okay. So how can we do that? Suppose we already have this convex hull. We're going to store the convex hull as a sorted set of points, sorted in a set, sorted by x coordinate. And we can prove that it's also going to be sorted by y coordinate, right? Because if there's something like this, then this point is going to be worse than this point, so there's no point in keeping it in the set, right? So that's how we're going to store it. And the way we do queries on this structure is, for example, say we want to query a point coordinate x, y. We search in the set the coordinate, the x coordinate. We find the first one that is greater and the previous one that can be done with iterators in the set. And then we take this line and check if the point is below that line or not. That's a geometric query. There are some special cases, like for example this here, before the first point we have to check this line. Okay, that's easy. And then we have to show how to update the structure when we add a new point, right? So the first step would be to check if it's already inside the convex hull. If it is, we can just do nothing because it doesn't affect the convex hull. And if it isn't, we can insert it into the set. For example, we insert it here. And then we have to the polygon changes like this, right? Which is no longer convex. So we have to update everything so that it's convex again. Which means deleting some of the points. For example, this point has to be deleted. The polygon becomes like this, which is again convex. And the way we do that is for the new point. This is a new point. We check 2 to the left and see if this angle is concave. And if it is, we delete the point. And then we do that again. This point and the one in the left, if there's any. We check this angle and see if it's convex, and if it is, we delete it, and so on, until either we run out of points or the angle is convex. We have to do the same here, right? Yeah, I think one edge case would be when the last point, we have something like this. Last point is lower than this first point. And in that case, even though we run out of points to calculate the angle, we still have to delete this one because we don't want decreasing edges here because of the constraints of the problem. We want this line, so we have to delete that as well. And that's how we keep the convex hull. Any questions?
Why is the complexity good enough? Because we might delete a lot of points.
Okay, it gets amortized because each point we delete and most points.
Okay, so it is still linear because each point can be different. Question.
In which data structure can you storage like the points because you need to access to the points, add and
Yes.
remove?
I use a set. So I use a XY structure. I code a structure for points which has X and Y, and then the comparator is by X, and then you store it in a set. And set supports the lower bound.
Ah, true.
The lower bound query, which gives you an iterator to the first element, which is greater than or equal to your element. Any other questions?
Okay. I just want to add, there's a way to remove points from the context tool, but it's not very nice and it is very heavy implementation. So there's a way to have basically dynamic context tool, but you don't want to do it if you don't have to. So if you want, maybe you can, probably you can find something on code forces how to do it. But there's a way. Okay, thank you very much. Okay, and other one of you. Which one? Someone already said I before, and I want to wait with I. Wait, I? Oh, you say E. Okay, I should be fine. How about you? F. Okay, F had more solved. So let's do F first, then I, then E. I know you are waiting for M.
So problem F?
I can hear you.
Problem F says that you have like some random event with probability P of success. And you have like some trials of this, right? Until you have K of the last N trials that cannot success, right? And N is like more than 6, and they ask you the expected value of the number of trials you have to do. So we can do like a recursion here. In our state, it's like last n minus 1 trials, right? So this is like initial if you have n equals 5. So you store last 4 trials, right? And the expected value when you are in this state, it's like, well, you got one, and then with probability P, you change to the next state that it's like shifting this left and adding a 1 here. So it's like this, right? Because last one was success and this one is not meaningful anymore. And the other case, it's like 1 minus P, and you got like the not success, right? You failed, so you shift but add a 0, right? And you can do this like for every state, and you have like a recursion, but it's like it has lot of cycles, right? So even this one you can see it easily, but if you go like from any other state, you get a cycle, right? And then what you can do is just like n is really small, the number of states is like this, 64, I guess. So then you can have like these are you can get them in a equation system, right? And solve with gaps or something like that in matrix. Well, you have to do first this little step to get this from here. So it's not so recursive, and you can solve it with gauss directly, and this is the answer, right? Because you start with nothing, and you go like just the expected value from nothing. And well, if you have like some number of ones that is greater than k, the answer is 0, right? Because you already won. It's like this, and k was 2, so 0, you won already. And so you can do this and solve with Gauss because this is really small. And that's it, I think. Was it clear?
Let me try to reiterate. So we have a system of linear equations on to the power of n variables and to the power of n equations. So we can use Gauss algorithm to calculate the values of these variables. So the total complexity is
Like this.
2 to the power of n to the power of 2. But n was very small, so we can do it. Okay. Any questions? Any other solutions maybe? It is a very classical problem. So we have some kind of dp, but it is cyclic, so we are doing some other stuff like Gauss elimination to solve this system of linear equation on this dynamic states. But yeah, it is very classical. Awesome. Thank you very much. Okay, let's do I.
Right? Well, in problem I, we had two arrays. We have two arrays, A1, A2, and they asked us the number of ways to partition these arrays in subsegments, like it is a circular array, such that the elements in each subsegment are the same, right?
So there's a way to permute all of the elements in the segment, so they are equal in both of the arrays.
Yes, and the statement guaranteed us that A was a permutation of 2. Well, so n was up to 10 to the 6, and the values were up to 10 to the 9, I think. The first thing we do is we compress these values so that there are between 1 and n. And there are multiple ways to do it, like we can put all elements in a vector, sort them, and find the position where each element is. So after compressing the elements, all of them are between 0 and n minus 1. And then we're going to generate n random numbers, or the number of distinct elements we have. We are going to generate a random number for each of them. Let's say we have an array H, and then H0, H1.
Can you make your font a little bit larger?
What?
Can you write a little bit larger letters?
Oh, okay.
Probably not visible.
Okay. We're going to generate up to n minus 1 random numbers, H1, H2, H, n minus 1. And then what we're going to do is we're going to replace.
So n minus 1 or n?
Wait.
I think
N numbers.
it needs n, yeah.
Yes, n numbers, because all can be different. Yes. And then we're going to replace each of the numbers of both arrays with the random number we generate for each one. And after we do that, like, we can assume, because these are random numbers, that two segments are the same if and only if the numbers, the sum of the replaced numbers are the same in both arrays. Like if we have here from A3 to A5, for example, we are going to check that H3, we're going to check that H A3 plus H A4 plus H A5 equals H B3 plus H B4. Like we're doing hashing, we're doing a sort of hashing. We hash each element of the array to a random number, and we assume that the probability of the sum being the same and the sets being different is very low.
Yeah. So yeah, we are doing some hashing, but we want to have hashing that is invariant to permutation. So
Yes.
that's why we have sum, because if the sum, we don't care about the order of the elements. Just for safety, you should probably do it several times, or like on several hashes, or like two different numbers, to make sure that they are actually equal. Because you might have some problems if you are very unlucky with hashes, and you might get very unlucky with this problem.
Well, yes, and yeah, that's it. This is a way to do multi-set hashing, like you said. Then what we're going to do is we're going to subtract the hashes from this array with the hashes from this array to generate a new array. Like the new array will be hash of the first element minus hash of the second of the first element of the second array. Then we're going to do hash of the second element of the first array minus hash of the second element in the second array, and so on. And now, if we have some segment with the same hash as another segment, then its subtraction has to be 0. So now we have reduced the problem to a new problem where we have an array of n numbers. The numbers can be very big, and we have to count the number of ways to partition it into several subsegments of sum 0, where the array is circular. And to do that, suppose our new array is C0, if a subsegment has a sum of 0, then if we get the prefix sums array of this array, the element in this position will be the same as the element in this position. Yeah. So, and if there is another subsegment of sum 0 here, it will be the same as the prefix sum on this position. And because the sum of all elements in the array is 0, because the statement guaranteed us that this was a permutation of this one, then if we have a prefix sum here that is the same as a prefix sum here, then this will also be a subsegment of sum 0. So what we're going to do is we make the prefix sum array of this array, and then we count how many times each element appears here. So if we have the sum, for example, this number 5 times, in the prefix sums array, then all the partitions we can make have to have endpoints at these positions, but we can delete some of these separators. And if this number appears k times, then the number of partitions is 2 to the k, which represents all possibilities of choosing or not choosing each separator, but we have to subtract all the possibilities which involve the whole array, because the partition has to have at least 2 elements. Which are the possibilities of just removing all separators except from 1? We don't want to consider that possibility, so we subtract k, and we also don't want to consider removing all separators, because that will also lead to only one segment. And so the answer is the sum of this k over all number of occurrences of each element in this array.
Was that clear?
Why do you have to use the array H?
Because if we use the numbers as they give us, there are maybe some segments with the same sum, but they are different sets. For example, I don't know.
So we are using some hashing.
Yes.
If we don't use hashing here that is decent, then we usually have some collisions. So you can say that some segments are equal, which are not equal.
Yeah, like using the hash of the same element, like using the numbers in the array, maybe we have 1, 4, and 2, 3, which will have the same sum, but they are not different. But using hashing, we have a high probability that if the sum is the same, then the numbers were the same.
Did you do double hashing or like random numbers until what number?
I generate a random long for each of the numbers, and then I added like modulo 2 to the 64.
Yeah, that's basically the same as double hashing on it, so that should be fine. But if you try just hashing on ints, I think it will fail. Because you generally have n square possibilities of collisions. So it may get problematic very quickly.
Any other questions? No, I don't know the exact probability of having collision, but I think it's very few because each of these numbers is uniformly random between like 0 and 2 to the 64. So I think it's safe enough.
Just to be safe, like maybe if I started to implement it, then I will do it in a general way so you can hash it with 5 or even 3 numbers, something like that. So you want to be absolutely sure. But if you don't want to waste time, you can try on long terms, and that more or less should work. But as I said, like there's like n square possibilities of collision, so you have to be very careful what you're doing here.
Probably it's safer to like take these numbers modulo something.
Yes.
But well, that did work.
Yeah. Maybe I just want to add one more thing. If you think about this problem, it is probably easier to start thinking about the array that is not cyclic. So you can do it like for normal array from 1 to n, and then the thing that we are doing the prefix sums, and we are taking if the prefix sums have the same value, like the difference between some prefix sum and some prefix sum is equal to 0, is also like a very standard trick when you have to do something on cyclic arrays. So it's easier to think about non-cyclic arrays first, and then extend this solution for the cyclic arrays. Yeah, and the trick for hashing with just taking the sum is also like quite normal trick to use hashing when we don't care about the permutation of the elements. That's also good to know. We can take other things, but adding them are probably is the simplest and the fastest way. Awesome. Thank you very much. Okay, we have I, and I think that's the last one that we have on. So let's do I. And then we'll suffer with the that's crazy. I think I removed all of them that were on board.
Oh, okay.
Okay, so I'll talk about problem E. First, let's go through the statement. They give you an array of they give you an array T1, T2, T3 to the end. And those are sizes of messages that you want to send. When you start sending a message, you have to keep sending the message until all the time it takes has expired. And you want to position them in a way where, let's say we do 4 of them. You have to position them in a way where for every segment of size X, there is at most 2 messages that are completely contained in this range, right? So for example, this is not a valid answer because we have 3 messages that are in a segment of size X. And the statement, the problem is asking for the lowest final endpoint of your configuration. So he wants to minimize that. Okay? So the first observation that we can make, I think we can keep drawing here. The first observation is that if we construct 2 subsets where there is no complete intersection of elements of where there is no way to pick 2 segments that are completely contained in a range of X. So for example, we separate the initial array into 2 different sets that have where for every range X there's only at most 1 element that is completely contained on it. Then the combination of both sets will be a valid answer. Does this make sense? Like, if we partition it into 2 sets, where every set we only make a condition for 1, the combination will give the combination for 2. And this is if and only if, but I won't prove it. But it's not hard to do it. You basically have to, for every configuration where there is at most 2 segments here, you have to construct a partition where this works. It's not hard, but it's annoying. So what we're going to do is try to...
Can I add one more thing?
Okay.
So we are trying to solve 2 sub-problems when we are doing the exact same thing, but we are saying that we can have at most 1 message that is completely in this set. So we need to first divide them into 2 sets in some way, and second solve this problem for at most 1 message in this window.
Okay, so what we're going to do is study what happens in this particular sub-problem. Okay? So when we take the first message, by exchange arguments, it's always optimal to send the first message at time 0, because if we don't send the message at time 0, we can just push it closer to that. And if we think about the range of size X that starts at time 0, we cannot make any other message that starts before X, right? So for the first message...
That ends before X.
Yeah, that ends before X. So our first message always bans this range of size X. So we can only put messages that end at X plus 1 or higher. And by exchange arguments, it's always optimal to put it at X plus 1. So our first message does this, but our second message, we put here, if we think about the range of size X, we'll put the right endpoint at X plus 1, but what it does is it makes such that instead of wait, let me construct my sentence. It changes the problem in such a way that instead of being able to put the endpoint at coordinate x plus 1, it will put the coordinate x plus 1 minus t of I, okay, this is t of I, plus x plus 1.
What if t of I is greater than x?
Okay, I didn't talk about this, but we are going to ignore every t of I that is greater than x, because they don't matter. And also, I didn't talk about this, but we're going to ignore n less or equal to 4, because this is going to break our idea. Okay, so for the first element, it always makes it such the range goes to x plus 1, and for every element that is after the first, it makes such the endpoint goes up by this amount. Okay? So given a set, we know that the best way to solve this problem is by putting the element where this is the highest at the start, where the size doesn't matter, and at the end, because at the end the right endpoint won't go any further to the right. Okay, so what we're going to do is take the four smallest elements, because they give us the bigger amount here, and we're going to say, okay, so the four smallest are here, here, and at the end of both sets, and here is no problem. And now for the rest of the messages, we are going to change their value from t of I to x minus t of I.
Maybe you can use a different variable.
Okay, so no.
Just to make things a little bit less confusing.
Okay. W of I. Okay, I can use v because it's easier to say. V of I is equal to x minus ti plus 1. Okay. So aside from those four smaller messages, what we're basically trying to do is partition the initial messages into two groups, such that the size of the biggest group is minimized, right? Because if we make a group where it ends here and another one where it ends here, our answer is this. So we want to partition our messages into two groups such that their sum is as close as possible to the sum of all VI's over 2. Does that make sense? Okay. So we reduced our problem for that. Can I work here? Yeah. Okay. So we reduced our problem to that, and there is a DP that calculates for certain values an O of n times max v.
Maybe I just want to add, this is just an abstract problem that we need to solve.
Yeah.
So there's a way to do it in n, okay, I think you can.
Yeah, but the problem is I didn't remember how to do this.
Okay.
So what we actually did was use a concept of random walks. Okay?
Ooh.
So here is the random walks problem. You are in the number line at point 0, and at every step you can with a random probability go either +1 or -1. Okay? And I want to know, for n iterations of that, what was the farthest you were from 0 at any point? So you can go like this, and this, and this. Not actually. You can go this, 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 this. And I'm interested in the farthest you went from 0. Okay? it is a known fact that for n iterations, it is expected that you go square root of n from 0. And this will be used, okay? So what we're actually going to do is a dp of I x, where for each prefix I, we want to know if it is possible to make a set, to partition the sets such that they have difference x between them. Okay? And because we can't do, and because this is, okay, let's call the size of this t, because the complexity of this dp would be n times t, we can't have this be very large, okay? So what we did was say that x goes from minus 300 max v to 300 max v, okay? And this won't calculate all possible solutions, but if we do a random permutation of the initial array, it is like we're doing a random walk where for every step we go max v to the left or max v to the right. So it is expected for us to go square root of n times 10 to the 4, which is around like 2 times 10 to the 6, and this is like 3 times 10 to the 6. And this past, we had to use bit sets.
Yeah, I wanted to ask how difficult was it to
What?
How difficult was it to accept this solution?
Actually, the hardest thing was trying to make this larger, because like for our first implementation, the best we could do was 100 max v. Then I did some optimizations and could take it to 200 max v. And with pragmas, we actually were able to make it 300 max v, and it finally got accepted.
Okay.
And that's it.
That is perfect. Okay. Any questions? Okay. I can maybe add some stuff to it because it is not something that was the model solution, as you can imagine. Yeah, but the ideas were on point except for the last part. So we wanted to first say that we can remove all of the intervals that are greater than x. We need to make sure that we maximize at the end, because like we need to remember about it, like the result cannot be smaller than the maximal length of the message. So we need to max at the end with the result. Then we are left with only messages that are lesser or equal than x. We try to solve this problem just for at most one message being in like this window. We realized that the order doesn't matter, because we basically have the same factor for the same. If we sum over all of the messages, then we notice that only the first and the last message is important, and the rest will be always the same with the same factors. We can even like permute them in any way, it won't change anything. So we want to make sure that the shortest will be the first and the last one, and then we need to have some intuition or have some or spend some time to try to prove it, that basically the problem for the at most 2 messages is having 2 separate problems for at most 1 message. It is not something that is very trivial, but you can spend some time to prove it, or you can just guess and see that it works. I also don't want to go into details of that, but it can be proven that it works. The last thing to do is doing the knapsack. So this is the normal complexity of this knapsack, but in our problem it will be n multiplied by x, which is too large, and we don't want to do it. There is an algorithm that, with the constraint that all of the elements in the knapsack are less or equal than x, so they are bound in some way, we can do it in n multiplied by x. and this is P. algorithm. So this guy is still alive, and I think he's a professor at the University of Copenhagen. But he's a specialist in knapsack problems. So I think he even wrote a book that is called Knapsack Problems or something like that. So you can try to find this algorithm. I strongly recommend. It is not very complicated and not very interesting, so it's nice to look at it and be like, just know that this algorithm exists, and then you can solve it using this algorithm in n multiplied by x. Because, okay, what we are actually solving is you want to make sure that the sum of these variables of the segments is the closest to, okay, sum of v I divided by 2 or something like that. Okay? So we are doing the normal knapsack, and then we are finding the optimal partition, and then for this partition we solve the problem separately. By solving the problem is just choosing the shortest one at the sides and then putting them, and then calculating this value, so it's not that complicated. Okay? I have to say, I haven't looked into this algorithm recently. I will try to take a look, or if someone wants to hear about it, maybe you can talk about it. Maybe not today, but tomorrow. But if I remember correctly, it wasn't very interesting, so we'll see. I'm not promising anything. Okay, we have two problems left. Problem B and problem M. I think no one solved this problem during the competition. I'm not very surprised. Let's start with M, maybe. Or maybe, okay, let's start with M. So, in most of the competition, there's at least one problem that is very technical, and this was one of them. I strongly recommend to at least spend some time to solve this problem, because it can give you the edge over some other teams. Because usually when some teams see such problems, which basically more or less we know what we want to do, but it's very complicated and there's a lot of implementation involved, then some people just drop this problem and don't think about it. But if you spend some time and try to solve like tens or maybe hundreds of these problems, then it becomes quite trivial to do. And then you can maybe even spend an hour to solve it, but you know that it will pass in the end. So we'll have one more problem than the other teams. So it is something that is painful, but it pays off. So I do recommend trying to solve this problem. So what was the problem? We are giving an array which was very long and had 2 rows, 2 by m, and we had some segments in this array that had some values. So for example, this might be segment of 7s, this might be a segment of 4s, this might be segment of 3s, this might be one single segment of 8, or something like this. And what we wanted to do, n was very large, 10 to the power of 9, if I remember correctly. And what we wanted to do, we wanted to try to find a path in this array that is of some fixed length x and has the maximum value, where the value is basically the sum of elements in this array. So for example, we can do something like start here. I have colors, so we can use them. Go here, 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 then go down, something like this. And we don't know where it ends, so let's just assume that it ends here. So it has something like this. Okay? Two observations that are very straightforward. We cannot do a lot of turns. So the maximum possible number of turns is 2. So this is what I did. So I turned here. Okay, I will call them U-turns. So I can do a U-turn here, and I can do the U-turn here, and that's it. I cannot do much beyond that. I can do 0 U-turns, so I can do only something like this. Or I can do 1 and do something like this. Or maybe even this. But we know that this is the only possible versions that we can do. There are some tricks to do. Okay, The hardest one is, of course, the one with the two U-turns. It is probably easier to implement 0 U-turns and 1 U-turn separately to not think about them. 0 is very simple, 1 is a little bit harder, but 2 is where everything is possible, so this is the most difficult one. So we'll talk about this one, and then we'll say that the rest is similar.
Can you do something like this?
Like this?
Yeah.
I think it was possible.
No, it's in the statement that you can only do U-turns.
Oh, okay, sorry. I will double check because I don't want to.
The roads have direction, like a straight.
Okay, you can make up to 2 U-turns, so you cannot do something like that.
And each side has the direction.
Yes. Okay. Oh yeah, because like you can only go here that way and here that way. Yeah, I forgot about this. Okay, yeah, so you cannot do that. Sorry. Okay, so how we can achieve that? So first of all, the array was very long, but the number of the segment was very low as well. So the number of the segment was n, and the n was something like 100. Maybe more than that? 200, okay. But significantly smaller than n. So we want to do something about this. So in general, when you think about this 2 U-turn path, it kind of looks like this. So we need to find some point when we are doing the first U-turn, some point when we are doing the second U-turn, and some point when we are starting, and some point when we are finishing. And that's it. So there's a lot of simplification that we can make, and we'll start talking about the simplification to make our code much easier. So first of all, if we know it will look like this, the only 2 options that we can have is either something like this, or something like, something like this. So there are 2 options. So what we can do, we can assume that the gap will be in the upper row, and then reverse the, or swap the columns, swap the rows, and do the same, and then assume that we are also solving this case. And it won't cause any problems, okay? So assume here that the gap is in the upper column, upper row, I'm sorry. So this is first simplification that we can make. The second simplification that we can make, let me name this, I want to name them as well as I had in the notes. Give me 1 second. Okay, that wasn't very interesting. So this is A, B, C, and D. And we have several ways where we can put these points. So first of all, when we think about A and D, so these points, we can say that at least one of them will be at the end of some segment. So this is, in this particular case, it is at the end of some segment. Why is that?
Because if you're not, you can expand one of, for example, you have here and here, and you are in the middle of segment. So this one or this one is bigger, and you can move.
Yes, so if we are not at the end of some segment, then we can move both A and D in some direction, so to make sure that they are at the end of some segment. Okay? It doesn't have to be here, like the segment might end, like this segment might end, not that is, okay, that wasn't very clear. So if we have something like this, and this is not at the end of some segment, it doesn't hurt us to move it a little bit to the left or to the right, like the whole thing, the I and D at the same time. Okay? So we can assume that at least one of A and D are at the end of some segment. Okay? So that is one. Okay, that was the first trick. The second trick, either A and D, or D, are at the end of some segment. So the third trick that we can do is we can assume that A will be always at the end of some segment. If that is not the case, what we can do is exactly reverse the whole array and then assume that once again A will be the endpoint. Okay? So we assume that A is the end point of some segment. If not, reverse the array and it will be. Okay, so we are assuming that A has to be at some endpoint of some segment. So we have n possible options to place A. So that is something. Now we maybe can focus on B and C. So I want to say something similar, that either B or C also has to be at the end of some segment. And the argument is very similar. If that is not the case, then we are just moving B and C to the point that they will be at the same endpoint. Okay? So we can say for either B or C are at the end of some segment.
When you say endpoint, do you mean like they start or the end?
Yes. That's a good word for that, like a border of a segment. Maybe it might be slightly easier, but yeah, I mean that. Okay, so we have this, and now we cannot do the same simplification here because we already reversed the array. So we have two cases. Case one is A and B are, I will use borders, it might be slightly easier, borders slash ends of some segment. Or second case, A and C are borders ends of some segment. Okay, so the number of possible borders of the segment is obviously 2n. So what we can do, we can iterate of all possibilities for A and B or A and C. So we focus only on this case, and once again we'll say the second one is equivalent. We need to implement that, but the idea is similar, so I will just talk about this one. So we are fixing some A, and then we are fixing some B. So we have these points somewhere fixed. So now we need to worry where we'll put C and D. So what we are doing, first we can put C at the same place where the A is. So okay, so I want to consider all of the possible paths, that is something like this. And then either we have a very small this thing when C is equal to D, or we have a very long tail of the snake when C is almost the same as B. Okay? So I want to consider all of these possibilities. And now the only remaining piece of the solution is to realize that we don't have a lot of points that we need to consider. Because what we need to consider is places when we, once again, start or end some segment. So what we will be doing is either we can do it, there's a way to pass it in, if we really optimize it, to just go 1 point to the right. So we are moving C by 2 points and D by 1 point. Okay, let me try to do it somewhere. So when we have something like this, what we can do, we want to keep the same length of this snake. So what we are doing, we can move the this location here. So we'll have this. Okay, let me move it the other way. It might be slightly better. So I'm moving this here, and then I'm moving this here. So the C is moved by 2 units, and the D is moved by 1 unit. Okay, it's probably like I implemented it the other way, so it is expanded in this direction, but it's probably the same. So you can do it probably in some n square if you optimize it clearly, but we can do it in odd n. So what we are doing is we try to find all of the, like for each point, we can find the next interesting point, which is either the end of the beginning of some segment. And then it's not that difficult to change the total sum, because we know which segment ended and we know like if other segments begin at some point. So we know what will be the difference between these two positions. And these are the only interesting positions. Okay? So we can have some kind of skip pointers. So for example, if we are here, we know where is the beginning of each segment. And then we have odd and interesting points that we need to care about. And there's like just some math to try to figure out what is the value of these interesting points. Or not points, but positions, or how the snake is located on this array. Okay? So the total complexity is we need to iterate over A and B, which is n squared, and then we have to iterate over all interesting locations, but we also said that the number of interesting locations is O of n. So the total complexity is O n to the power of 3. Okay? I maybe a little bit, this part was hand wavy, but you can see that it is doable, but just like you need to spend some time to implement this. There was, like, I saw some solutions that had some worse complexity, so as I said, optimize n to the power of 4 could work, because the time limit wasn't very tight. But there's a way to do it in n cubed. Questions? Okay, if not, once again, this was a heavy problem for implementation. You have to waste at least 200 lines of code to implement it, but there's nothing really special about it. Like, these are all tricks that we probably solved several times, that we need to reverse, we need to only consider the beginning or the ends of some segments, so there's nothing that special, but you need to spend some time to implement it. So once again, I encourage you to try to implement it after the contest. Okay. So that was M. If I remember correctly, no one solved it during the actual contest as well, so don't feel bad about it. Like, it was kind of a problem that you don't want to solve if you have other problems. Especially if you have B, that you can write a lot of heuristic. So I saw a bunch of tries to solve this problem. We have about 15 minutes left, not bad. So in this problem, we are given some number of chocolates, and these chocolates were all rectangular. So we are given, like, for example, we have chocolate 2 by 3, we have chocolate 3 by 3, and more of them. There were some limits on the size of the tables and on the number of them. Okay, so the sizes were A times B, where A and B were no greater than 6. And we had at most 50 chocolates in total. Not pieces of chocolate, but tables of chocolate. And there was also another restriction that, okay, we want to divide this chocolate between 2 grandchildren. So what we want to do is to divide this set of chocolates into 2 groups of equal sizes, or the equal sizes of the number of chocolate pieces. And what we can do, we can divide the chocolate by cutting through a straight line. So we can divide it into 1 times 3 and 2 times 3. And we want to, there's a limit, like, what was the T? One more. I got confused myself. Okay. Okay, I said something else. So we are looking to generate two exactly the same collections of chocolates, but the limit is that each of this collection has to have at least t when t is some fixed number in the input chocolate pieces. Okay, so in this case we either need to have a different 1/4 piece, and then this might be one collection and this might be the second collection, this element and this element. And we might have some spare chocolate that we are not giving, I hope. Okay? Questions about the problem? When it was confusing a bit, but I think. Okay. So what was the idea that I think some of you started to implement is there was a problem with one assumption that is slightly tricky and a little bit misleading. So we can assume that in some cases we may not want to do divides. Okay, if we have a pair of exact same tables of chocolate, so for example when we have 2/3 and 2/3, the obvious thing is to not divide them, but to give one to one child and the other to the other child. This is incorrect. We cannot do that. Does anyone during the competition came up with a counter example for this? I have one already, but maybe someone did. Okay, so let's consider 3/2. That was not good. 3/3, 1/5, 2/5, and then 2 times 3/5. So as I said, the very wrong assumption is that we can say that this will be one collection and this will be the other collection. But this is not the case if, for example, if we divide this into 1 and 5 and 1 and 5 and 2 and 5, and then we can divide it into 3/2 and 3/3, then we can only use two splits. So we are splitting this once and this is our second split, and then we can use this as one collection and this as the other collection. Okay? And this is the minimal and optimal answer, and we cannot achieve that without splitting these two tables of chocolate. Okay? So this is the counter example for this assumption. But did someone try, if you think about this assumption, then you can think about some dynamic programming on some number of chocolate, because then we have either 0 or 1 of each type of chocolate, and the number of different types of chocolate is also very small. So you can have some kind of dynamic programming on 2 to the power of number of different chocolates, and then we have some kind of dynamic programming that is solving that. Did someone try to implement that? Okay. Okay. You too? Okay. So if you implement it, it is bad because it won't pass, but you can try to run it on some random generated test cases, and you can notice that the number of splits that you need is not that large. Did you try it? Yeah, 9 is the upper bound for that. So we know that the upper bound for the number of splits is at most 9. So what we can do with this knowledge? Just think about it. Think that the number of, if the number of splits is no more than 9, and the number of splits that we can do on one table of chocolate is at most 5, because this is the limit for the size of the table of chocolate, then maybe some kind of recursive solution will work. And it will work. So what we have to do is we have to do the almost most trivial brute force solution when we are considering all of the tables of chocolate, but we are bounding the branches of our recursion solution by the maximum answer. So you know that we don't need more than 9 possible splits. So if we are trying in our recursion to do more than 9 splits, we are just saying, okay, cut the solution here and don't try to expand this node in our state of things. And when we have this bound, we know that it's not that easy to prove, but we can show that the number of states that we actually have to visit is not very large and it fits into the time limit. Okay? So the solution is a little bit disappointing, I would say, but we need to do some recursive solution that is bounded by the number of cuts that we have to make. And that's it. That's the whole thing. Like I see on your faces that you're also very disappointed about this problem, but this is the solution for this problem. I can tell you that during the actual contest, during the first 4 hours, it was solved by only one team after an hour or 20 minutes. And after that, no one solved this problem at all. So one team decided to implement the brute force solution, it passed, but then other teams maybe thought that it's an easy solution, like some kind of maybe dynamic programming or something like that, but during the competition, no one succeeded. So yeah, don't feel bad about this problem, but it was quite tricky, and as I said, solution, for me it was very disappointing. Questions? But it is good to first try to implement this dynamic program, because we have this upper bound, which is very helpful to understand why is that something that may pass. Okay, if there are no questions, let's have a break. We can start 10:15, and please try to be here on time. Thanks a lot. First of all, someone pointed out that I haven't uploaded the links to the problems from when. So I didn't give you the links, but I gave you the problem statement, so we should still be able to talk about that. Oh, and I talked with Jonathan yesterday, and he is very excited to come here next week. Okay, the first one, let's start with the easier one. If you remember, the easier one was prefix suffix. And the goal was giving some words, A, B, C, A, B, C, B, A, B, A, B, B, A, C, A, B. The goal was to find the longest prefix suffix or border of this word, but we allowed the border to be the cyclically equivalent to the okay, so the suffix can be the cyclic rotation of the prefix. That was allowed. Okay, and we want to do it with some maybe an log n or something like that. Okay, did someone think about it and had some interesting ideas? Okay, do you want to say that about?
Yeah, so using the same idea as he explained for problem I, so you just hash the characters and then you do partial sums to.
Okay, yes, that is correct. Like hashing is the easy, maybe not easy, but one way to solve this problem. So that is not an interesting way to solve the problem. It's not clear. Okay.
Use order independent way to combine character hashes. Just like in problem I, you just add them up.
But this is permutation of cyclic.
Oh, this is a cyclical. Okay, this is.
There's a way to do it like do hashing with cyclic rotations.
Okay.
Okay, we can talk about it, but I still want to find if someone has a different solution for this. Especially I'm looking for something linear that is not very painful to implement. Okay, I will give you some ideas and you will try to tell me why is this idea stupid or is it not stupid. So I want to take this word and I want to divide it into two smaller words, and each word will be exactly the half of the original letter. So I'm just taking something in the middle, and if it's not in the middle, so if it's the length of the word is odd, then I just don't care about the middle letter. So I just like exclude it at all. So I have A, B, C, A, B, C, B, and the other word is, I think, C, A, B, C, A. Okay, it was actually even. So it will be A, C, A, B, C, A, B. So this might be W1, this might be W2. Okay? And what I want to do, I want to reverse the second half. So now I have B, A, C, B, A, C, A. So that's the other step. And then I want to have the convolution of these two words, of W1 and W2 reversed. So I'm taking the first word from W1, the first letter from W1. I have A, then I have B, this is the first letter from W2 reversed. Then I have B, then I have A, then I have C, then I have C. Then I have A, then I have B, then I have B, then I have A, C, C, B, A. Okay, I did something, but why I did it and what was the purpose of that? Yes. No. No as an FFT, but I'm just taking, I think that's the right word. The convolution of two words is basically taking like we are taking the letters from each word, like one letter from this word, one letter from this word, and so on, so on.
Interleaving?
Maybe that's better. But I don't want to go. I know the word from that in Polish, and I think it is the same as the word in FFT. So I will double check later if that's the right word, but I think it's true. Okay, why did I do that? Why did I do that, and what was that? Ooh, I've heard a nice word. Okay. But why?
Because, like, when you have a prefix that is a cyclic permutation of the suffix, then that permutation can be split into two parts. Like every cyclic permutation is splitting the string in two and reversing those two parts, right?
Can you say it again? Like
every cyclic permutation of a string is splitting the string into cycling the string into two and then reversing those two cycles.
okay, yeah. So if we have some words, let's call it X, and then we want to divide it into, like we want to make a cyclic permutation. So what is happening? We are taking, I need an example. It's probably won't work here. So I'll take T1, T2, T3, T4, T5. And then every cyclic rotation of that is T3, T4, T5, T1, and T2. So what will happen, like, wait, so you wanted to say that like now I have a, no. Okay, what I want to say, if I want to take the convolution of these two, so this is T rotated, let's call it that way, and then I want to consider what will be the convolution of this. So now I'm reversing this one, and I have T2, T1, T5, T4, T3, and what is happening is I will have two pieces of the same word that are rotated. So this is rotated and this is rotated because we know exactly where was the cut. So if I reverse it, then we'll have the cut here, and what AB that is reverse is B reverse and A reverse. Okay? Nothing special happened here. So now, when I have this convolution that I will keep using this word, maybe I don't know what it means, then I will have T1, T2, T2, T1. Then I will have T3, T5, T4, T4, T5, T3. So what I have is basically two palindromes. This is a palindrome, and this is the other palindrome. Okay? Is this enough to check if I have a cyclic rotation?
They have to be even, right?
Yes, that is one thing. So I need to check if I have two palindromes of even length, that their length is equal to the size of the original word. Okay? And that's the only condition I need to check if I have the cyclic rotation of some prefix suffix. Okay? So in this original example that I showed, I'll have ABA and CC. So I'll have two palindromes, both at even length, and they all form like the sum, like they form the prefix of size 3 multiplied by 2. So 3 will be the answer, and I want to say that 3 is the prefix suffix that is the maximum prefix suffix that I can get. It might be that there might be other two palindromes that are longer than that, but I want to take the maximum one, the maximum in length. Okay? So this is the idea. We are taking the convolution of these two. So now the only thing that remains is to find the palindromes in some meaningful way. And how we can do that? Yes, mana, that's the answer. So we are trying to find the all of the palindromes, and it's easy to have some kind of like pseudo-dynamic programming to find the maximum one that is fulfilling this condition. So first of all, we only need to find the even palindromes. So we are taking half of the mana away. And then we want to make sure that we can find some two palindromes that are connected with each other, and the sum is, and that's it. Like the sum of length is maximal. Okay? So it might be something like this. It might be something like this. But as we can find all of the palindromes, that is like fairly simple to find in linear time the maximal one. Because we know the radii of all of the palindromes. So it's fairly simple. Okay? This is a trick that I have chosen this problem because it was the simplest problem that is using the trick. And I think it is kind of magical that we started from something from prefix suffix, and now we are finding palindromes in some word that we generated. So I find this problem interesting. Questions? Okay, how to do it with hashing? I have to say I hate hashing, but let me try to think about it. So we want to make sure that we have some kind of hashing that doesn't care about the cyclic rotations. How it was done? Yeah.
Can you hash the transitions? I mean, if we have two strings have the same transition, I mean, have one letter after other in the cyclic view, they are rotations. I mean, A, B, C, the transitions are A to B, B to C, and C to A. I'm not sure if two strings have the same transitions, same histogram of transitions, they are cyclic rotations.
taking overhashes for substrate and then running all of the for all cycle permutations, running the cycle.
But then, but then it will be quadratic in some way?
No, you can do it single, but that actually just gives you. I mean, I assume you all have something that goes over. Yeah, so that just gives you the same as like the multiple times. It's just the sum of the powers times the sum of the elements. That's really what it is.
Okay. I think you, okay. Let's talk about it tomorrow because I honestly wasn't prepared to talk about hashing here. I will prepare myself a little bit better. So I probably could do it in like 10 to 15 minutes, but I also don't want to waste your time. So let's do it tomorrow, and I hope you're happy with this solution. I was hoping that you would briefly mention hashing, but I wasn't really certain. Okay, that was one problem that was really magical. The other problem, if you remember, was I don't know how I called it. Template? Or pattern? One of these. So the idea was we wanted to find the shortest template / pattern that we can cover our work with, but these coverings can intersect each other or overlap. So when we have something like this, maybe the pattern will be ABA, because we can cover this wall like this, 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 and this. Okay. Any thoughts about this problem?
I have some ideas which lead to a very ugly solution in n log n.
Can you repeat the last sentence?
I have some ideas that lead to a very ugly solution in n log n.
Okay.
Does not involve hashing.
I like that it doesn't involve hashing. Okay, does someone else want to talk about a little bit about this problem? Okay, I know at least two solutions. One is fairly nice n log n solution, but it requires some proofs. And one is fairly nice but very complicated linear solution, but we'll talk about this linear solution because it's also magical and I want to talk about it. So any other people that want to say something about this problem?
N log squared using like FFT and binary search.
Why? I mean, I hope it won't pass. I just want to say this. Okay, let's hear N again.
Okay, so first, you know that the template is always going to be a prefix, right?
Yes, that is like fairly straightforward to notice, and this also gives us a very simple quadratic solution.
Okay, and what you want to know is for each position in the string, how long a prefix you can make, which is also a prefix of the whole string, right? You want to calculate that first. You can use a C function or something like that.
I didn't understand.
So you take a number I. You want to know the largest prefix of the string,
Okay.
which is also a prefix of the substring that starts at position I.
So you're saying if I have, let's say this is I, this is I. So you want to think what is the template of this one?
The largest prefix of the whole string, which is also a prefix of that string.
Okay, so let me try to write it. Largest prefix of W. So it will be W from 1 to I. That is also a prefix here of W a plus 1 to n, something like that.
The first
Okay, but this prefix is, this is the prefix. So the prefix of the whole word, but I just called it from 1 to I. So I'm saying the I is the...
But it's not the same line.
Oh, it's not the same I. Okay, that's what I didn't understand. Okay, so this might be the prefix of the whole word, but it also has to be prefix of this thing.
Yes.
Okay, now I understand.
So that can be calculated, for example, with LCP. That I believe there's also a simple calculator. That's the Z function.
Okay.
Okay, and once you have that, you can simulate like increasing the prefix you take and simulate what happens.
Okay, that I understand now. And it is in the right direction, but there might be something even simpler. So you said something that has to be a prefix of the original word. I want to go a little bit beyond that. I want to say that it has to be also a suffix of this word. So it has to be a prefix suffix. That's one thing that is fairly straightforward. So one other obvious way is to check every possible prefix suffix, but it can be also the linear number of them. So for example, A, and all A's, but we can also add some B in the middle just to mess with everyone. Okay, so we know that the number of different prefix suffix can be also linear in size. But the question is, do we need to check all of them? Okay, so we said that it has to be, well, has to be prefix, 2 has to be suffix, the third thing, do we need to check the mode? And the answer is no, I can give you that. But now, in what way we can limit number of different prefix suffixes that we can check?
If it's a pole of another prefix suffix, we don't need to check it.
Yes. So the claim is, I hope that's what you said, because I haven't heard it that well, but I think you said that if we have a prefix suffix, okay, let's say AB, 2 borders or prefix suffixes. Then if A, the size of the length of A is greater, okay, if length of A is smaller than B and the length of A is larger than half of the size of B, then we claim that we don't have to check which one of these.
I didn't cite that.
Okay, so sorry.
I cite that if B is equal to A concatenated A, we don't need to check B.
Okay, so I went a little bit beyond that. So I said that it is, okay, so you said that if we have B equal to AA, then we need to check that. Then we don't need to check which one, A or B?
We don't need to check B.
We don't need to check B. So I'm going a little bit beyond that. So I'm saying if A just has a length of at least half of B, then we don't need to check B as well. So I went a little bit ahead of you, but it was in the right direction. Sorry, I probably I shouldn't. Okay, so why is that?
Like you know that B is going to be a suffix in the prefix of A as well. And if the length is at least half, then it's going to cover A. So anything that can be covered with A can also be covered with B.
That's exactly it. Let me just try to do something. I think I have a nice example. Boom, boom, boom. Okay. this, and B is this as well. So now we have A that is at least the half of the size of B. So it is something like this. Okay? So if we check A, and it is not a template, so that means that A has to be covered, like A had to cover this in some way, because A is also here, because A is here.
No, it would be.
It's at the end because it's also B.
Yeah.
Oh, yeah, because it's here. I was thinking about time of the moment. Yeah, but because this is B and this is B, so A has to be here as well. So if we are not able to cover everything with A, we are not also able to cover the whole thing with B. So we can also only take A, and if A doesn't work, then we need to take, we don't have to take B. So we have a very nice condition for taking prefix suffixes. We need to take only logarithmic number of prefix suffixes, because every time we increase the length of the candidate by at least 2. Okay, and that eliminates a lot of them, and the solution is L again. And it's not, it is kind of a nice solution. The only thing we need to do is to generate this prefix suffixes, and that's quite nice. Is it clear how we are checking the candidate? Maybe I should also mention this. It's some kind of like very simple, maybe I want to say dynamic programming. Not greedy dynamic programming. It is dynamic programming. Yes.
Why is it answer
With A and B, those final matches and make sure that they.
Yeah, but like you need to, like on KMP, you need to verify that the, okay, you need to verify that I can go, okay, I have the pattern matching that is showing me these patterns, but I need to make sure that these patterns are covering the whole world. So I need to go from here, I can skip here, then I need to find something that is, yeah, like maybe 1 pointer even, I would say. But yeah, we need to do something like this. Okay? I just wanted to make it clear that we know how to do it. Okay, so that was L again, which wasn't that nice. So now let's think a bit about linear solutions. So the clue or the hint I want to give you is, once again, in text algorithm everything is connected in some way, and this algorithm is also, okay, now we want to calculate, like we want to be able to say what is the shortest template for each possible prefix. So the goal right now is to have some kind of iterative algorithm that knows the answer for let's say W1, Wi, and from this we want to go to add one letter, Wi plus 1, and get the answer for this whole word. Okay? So now we will be adding new letters, and we want to somehow rational about the whole template for the whole word. It wasn't like a very huge clue, but I want to show you in which direction we are going. Okay? So let's think about it, and to think about it, I want you to make some manual work and try to do this example and try to calculate this for every single prefix. It will be slightly painful, maybe not that painful, but I want you to go like through every single letter and see what will be the shortest pattern or template for all of these prefixes of this word. Okay, so for the single word it will be just 1, for AB it will be just 2, for ABC will be 3, for ABCA it will be 4, and so on and so on. 4, is it correct? Yeah, it is correct. So it's not interesting, but it will, like here it will be 3, because I can use ABC, ABC. I can also, okay, maybe this is not the greatest example, I will give you a little bit more interesting example. Where is it?
What is the difference in the place and for the weight?
Okay, I will give you A, B, A, B, B, A, B, A, B, B, A, B, A, B, A, B, B, A, B, A, B, A. Maybe add BBA, BBA. BBA, BBA. Okay, so that's the law. It is quite long, but not very. So I thought you would be able to do it in less than 2 minutes. Like you need to do some manual work to have some observations. Like I cannot imagine just looking at this and came up with these ideas. And it is something that is, I think, very helpful in terms of text algorithms, that you need to look at some examples, try to think about some answers for these examples, especially with these palindromes. Like, if you remember the problem about palindromes from Wednesday, it is fairly simple to notice that we need to only think about the, what was the word, not factor, the period of the palindrome. Because it's very hard to generate an example that is not trivial. You even saw, like, my example was AAA, because I couldn't think of anything that would be on them. There's something similar here. Like, we need to think about it for a moment, we need to consider some of the examples, and maybe we can figure out some solution. I hope I did it right, but I think I did. Okay, so does anyone have the whole thing? In Python here.
Okay. 9. 15. Okay. That's how far it goes.
So I think this might be 8. I hope it will be 8. Is it not 8?
Oh, that's an 8.
Yeah, it's also only 18. Sorry. Something was not clear. This 8.
I thought the last character was a C.
Sorry. Okay, complete. Uh, 19, and this is 20. Okay, did someone get something similar to what I did? I didn't check that, but I think it looks okay, but you can correct me if you see something that is ridiculously bad. Okay, so now we need some observations based on that. First observation that is rather trivial. Quite often we get the answer equal to the length of the word. And it is very often. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 15, 16, 17, 18, and 20. Okay?
Could you check the last 8?
Sure. I said maybe I did something wrong, but I think it was okay. So I want to say that A, B, A, B, B, A. Then this will be this. Oh, you might be right actually. Because I cannot cover this one.
Yeah, it's not a prefix, I think.
Yeah,
Not a suffix, it's not a prefix, I think.
I messed something up. So how we can make it better? Where did I make it mistake? It's not that important, but I specifically wanted to show something that is showing some interesting cases. A, B, A, B, B, A. B, A. B, B, A. B, A, B, A. Wait.
You didn't take the 8. You said 8, but you're only taking the 6.
Well, here?
No,
No.
it says if you add to graphic size 6, but you said 8.
Oh, okay. Yeah, you're right. 2, 3, 4, 5, 6, 7. I want this one.
Yes.
Okay. Then it makes more sense, I think. So this will be this. And then this will be this. So the answer for this one I think is still 18, but this will be 8. Okay, now it makes sense. Yeah, thank you for that. That's why I probably should also prepare this one, but I was a little bit lazy. I was counting on you. Okay, any other differences, but I think it might be good now. Yeah, I really wanted to have this to be equal to 8. I'm glad it is equal to 8. Okay, so then these are the places when it is equal to the length of the wall. So now let's take a look at all of the other things. So all of the other places when it is not equal to the length of the wall. What we can say about these elements?
They all point to predictions that are equal to them.
Yes. Like it is very, like it has to be a prefix suffix. So it's like that is a good observation, but not that important right now.
That number must have appeared before underlined.
Yes.
For example, 8 in some positions, then 8 positions afterwards. You have to have 8 or maybe less.
Can you have okay? So this 8 happened again like 8 places before, but I think it can be also happen like someone. Okay.
It is 7 places because there's an overlap of 1.
Yeah, so I'm saying like it doesn't have to be exactly 8 positions before, but it has to be like somewhere here, like in the last 8 places. That is correct. So maybe I will try to hint you in the right direction again. So can we think about prefix suffixes of all of these locations when this is not equal to the length of the word? Can we say something about that?
The overlaps have to be palindromes?
Not really.
No, they have to be prefix suffixes of the
That's more like it.
of the thing. The pattern.
Okay, is it clear for everyone? So we want to say that if some word is a prefix suffix, maybe I took a picture for that. Okay, maybe let's first do something like this. Sorry for that. So let's have a whole word, and let's say that it has some prefix suffix v. One moment. Okay, now I want to see. Okay, so we have v, that is a prefix suffix. And we have a w, which is a template for, I wanted the template for let's call this whole thing x, and this will be the template for x. So the first thing I want to show, if v is a template for x, v also has to be a template for v. If w is a template for x, then w also has to be the template for v. It is fairly simple. So when we have v that is w that is covering the whole thing in some way, so I want to make sure that it also covers v in the same way. So it doesn't have anything like this, because then it won't be a template. Okay, because the last thing can go beyond that. So I want to show that this is not possible. Why it is not possible? Because this is a prefix suffix of the whole word, v. So it has to end here. Like v is covering the whole word, so it also has to cover this part. So that means I can take this part and put it here. So I cannot have a situation that I will be left with something that is going beyond this. So there might be something that is going beyond this, but there's also something that is ending at this point. Okay? So that proves that if V is a prefix suffix and W is a template for X, and I should probably say that the length of W is lower than the length of V, that means that W is a template for V. Okay? So this is a little bit, I think it's similar to what you said, but if something is a template for the larger word, it also has to be a template for the prefix suffix.
It was a little bit less, but I think.
Yeah, I know, but okay, so that is first step towards the solution. And the other step towards the solution is to say that we only need to check the template of our prefix suffix. Okay? So the theorem that is the key for the whole solution very important theorem. I will also use the same notation that I have here because I'm too lazy and I want to do it. So, well, right, actually. If the shortest template of the word of the prefix suffix of X. So X is right now the whole word, and the prefix suffix will use the same notation as here, it will be V. So if the shortest template of the prefix suffix of X is not a template of X, then the template for X is X. Okay, so what I'm saying here, that I only want to consider something, I only want to consider templates of the prefix suffix, and if that's not the case, if the prefix, the template of my prefix suffix is not my template, then I don't have a template, or my whole word is a template. So more or less I can look at this example. I'm here, I'm looking at my prefix suffix. Do I have any good prefix suffix? I have ABA, for example. So I'm looking at the template of ABA, which is ABA. I need to verify that this is not typed prefix suffix, because it might be, but if it's not the case, that the answer is 15. And vice versa, if I have a prefix suffix that has a template, so for example, let's look at this word, something like this. So I look at some prefix suffix of this, which is ABA, BB, ABA. I need either more colors to try to mark that correctly. Okay, so this is a prefix suffix of the blue word, and then I'm saying if this is actually a template for the whole word, then I already know my template as well. And that's the only option. And maybe some other example that is not that trivial. Let me try to find something. Five is trivial. Oh, 8 here is trivial. So we have exactly two possibilities, like two prefix suffixes. So one prefix suffix is this thing. So then the other thing will be this one. And I can verify that the template of this is equal to 8. So this is also my template. But I can also look at the other prefix suffix, which is in this whole thing. Okay? So I'm looking at the pattern of this prefix suffix, and I also see that this is 8. So I know the shortest template of my prefix suffix, and I also know that this will be either this or the whole word. Okay? This is like some example of this theorem. How to prove it? Like we see that it works. Like I show you examples that it works. But now the question is why?
Because of the last theorem you proved.
Yes.
You take the smallest prefix suffix of the whole string, and if it's the whole string, then you already have that confirmation. And if it's not the whole string, then it has to be a prefix suffix of the whole string. So it has to be shorter than the largest prefix suffix. Shorter or equal to the largest prefix suffix.
Okay, it is slightly more complicated than that, but yes, like we need to consider some cases like if there are some lengths that are not that trivial. Like so for example with the maybe it is oh wait a moment. Yeah, but yeah, we there's a reason why we prove this first. So we want to take a look at the smaller template. We can show that if it is a template of the shorter word, that it has to also be template of the larger word. If this is not the case, then we cannot find anything that is a template. Because then it also had to be a template of this of our prefix suffix. Okay? That's
So you have to show that any template of the large word has to be a template of the prefix suffix.
yes.
Except when it is the whole word.
Yes.
That's what you proved there. Because that template has to be shorter than or equal to the largest prefix suffix because the template is the prefix suffix.
Yes. So when I look at exactly the last prefix suffix or the longest prefix suffix, that is enough. Because if, like, even if I have smaller prefix suffixes, I don't care about them because the smaller prefix suffixes are also taken care of. So what I'm doing in my algorithm, more or less, is I'm looking at the longest prefix suffix. I'm checking this particular template because I already calculated that because I'm going from left to right. Then I know what should be the template of this whole word because this is my only candidate. I know how to check that because once again I know how to check it in general. So I just need to check if this is the word. Like if I cover this remaining part with my template, and that's it. That's the whole algorithm. So if this works, if my check works, then the answer is equal to the answer of my prefix suffix. And if it doesn't work, then the answer is equal just to the length of the word. I see like a lot of expressions on your faces, including boredom, surprising.
How do you check that something is a template?
That's the next thing that we want to talk about. But I want to make sure that this is clear more or less what we are going for. Okay, is this clear? Do you believe in everything I said?
Can we do a quick recap? Like,
Okay.
what is the claim here?
So the final claim is that we have only two possible options for the template of the word. The first option is the template of my longest prefix suffix. So this is more or less because we show that if there's a template of this of my prefix suffix, okay, if I have a template, then it also has to be a template of my prefix suffix, any prefix suffix. So in particular, I can only take the longest one. So that is one option. And the other claim is basically that we technically didn't prove, like well, technically we did prove, but I a little bit skipped some parts, but I don't. Okay, let's keep. The other option is that I don't have a prefix, the template at all. And then the only template I can use is the whole word. Okay?
Yes.
Like I agree. I skip the part when they show that this is the other option, but it is the other option. Like you can even see on this example. Like if you want to prove it, you can. There are like two cases you need to consider, and that's it. Okay. So then we know how to calculate that. We first calculate prefix suffix of every single one. So you can use like prefix function or something like that. Then we know where we need to take, like for example for this one, we are taking the value of here. The one missing piece that we will talk about in a moment, which is not very difficult, is how we want to verify that this template of this length is covering this part. If it is, that means that it is our prefix suffix, this is our template, and if it is not, then our template is just the length of the word at this point. Okay? Awesome. So we have 15 minutes to talk how we can verify that this candidate from our prefix suffix is indeed our template. And it's not that difficult. Come on. Like, take a note that, okay, if this is a prefix suffix, in this particular case, so it is here and here. So it's not that difficult to check that. So it's not like one if, we need to have a separate array with something to keep track of something.
It needs to be all of one, right?
Amortized. I wanted to go before you came up with the solution because it's not that difficult. And I will start writing something else on the other board.
So what you're saying is that the answer is there are only two possible answers?
For the, okay, at the given prefix, Yes, there are two possible answers. So it is either the answer of my longest prefix suffix or my length, and that's it.
Okay.
So I can even look here, and what will happen is when I have something that is not, I basically copy the answer from my prefix suffix. And that's it. And 8 will be this one. Okay, so any clues how we can determine quickly how we, like, if we are covering the whole word with our template? So okay, I can give you another hint because I want to finish this class at some point. So we want to store how long of a word we can cover with this particular template for each template separately. That's the clue. I think I understood. I think I have, and then something I didn't understand.
I think I have the solution.
How complicated is it?
You were asking for solutions?
Yes.
It's not. No, not that complicated. So you want to check, like you want to check if something is a template, right?
Yes.
And for something to be a template, that has to be a template of another string, which is not very far, right? You have to be able to cover the remaining distance.
Yes, but like it doesn't have to be like not very far. It's like very loose condition.
At least greater than or equal to the length of the template you're checking, right?
Yes.
But you can also check if there's another within the length of the suffix prefix, because you know that the suffix prefix you can cover.
Yes.
And the edge of the suffix prefix moves monotonically.
Even more than monotonically.
Moves to the right, so you can.
Okay, but so by some fixed value even. No? Why not?
Like the K and P number moves monotonically to the right.
Okay, I think I see, but
you take the string and the prefix, and then that copy is also suffix.
yes.
The beginning of that suffix moves monotonically.
Why monotonically? Like it moves to the end of the word.
Yes.
Okay. Why monotonically? Okay.
That's what I thought.
Okay. So basically, like we'll have a separate. Okay, I want to show it how I feel about it. So for each template, we know how long we can cover it. So for example, basically at the very beginning, each template is covering just it. Like a template of length 2 can cover this part. But now, when we notice something that maybe it is right, then we are checking if the template of this part is reaching the previous one, because we are taking the prefix suffix of it. So if we can reach the previous coverage of this template by prefix suffix, we know that it has to be here as well.
Yeah.
So we'll call it range of the template. It is very small, but range. So if we can, like if our prefix suffix is reaching the range of the previous template, that means that it will also be our template. Okay, so the only thing that we need to check, like this, okay, I will also like look here. So for this will be range for the 2 words template. But for the 8 words template, at the beginning this will be equal to this. But then, when we are checking here, we are checking prefix suffix of this one, which falls somewhere here. So the range of this template is beyond the prefix suffix. So it also, the range goes here as well. We know that this whole thing can be covered by the template of length 8. Okay? So the algorithm is like painfully simple, I would call it that way. So the only thing we are doing is, I will even write a pseudocode because I want to show how simple it is. So algorithm is as follows. For e equal to 2 to n, S is a template from prefix sub, okay, I will call it ref from I, and then there's one condition I need to check. If range of S, if my range is at least to my prefix suffix, so if I'm basically covering everything except for the length of the template, so there's another instance of that I know will be also here because it's a prefix suffix, then template of I is S and range of S is I. Otherwise, template for I is I. That's it.
But then when you update the range of a certain template, don't you also have to update the range of all the templates?
No, because I don't care about the other ones. So I just care about the template that I will be using.
But for next iteration, like for example,
So I know that 2 won't be here. Like if I cannot, okay, I cannot cover this part with 2. So I will never be able to cover this part with 2 as well. So I need to cover, like I need to only care about the template of my prefix suffix. You don't seem convinced.
for my iteration, I only need to care for that one. But maybe.
Yeah, I'm not saying like maybe there's like okay, it is very difficult to think about example that we will have like 2 templates like going together, and I think that might not even be possible. But I'm saying like in this iteration, I only care about this template, and that is enough. Okay, I forgot about one thing here. I need to check if I have a prefix suffix, and prefix suffix is not equal to I, so it's not the whole world. But that's the only thing I need to add. Okay, it took us a while, but I hope you see why I really like this algorithm, because it's like when you implement it, it's 6 lines of code, even less than that maybe. It is very magical, like this is very magical, and if someone tries to look at your code, they don't understand in most parts. But this is a very common problem. I think I saw it at least 3 times on 3 different contests, and you can also, like, as I said, like you can extend it and try to do it. You need to give me the answer after getting another letter of this word, so you can be even interactive in a way, because I don't use anything here at all. So I really like this problem, I wanted to share it, and I hope these 2 problems about the solvent you also find a little bit magical. We don't have that much time left, so I will give you a homework for tomorrow. In this homework, you will be giving some places when we can put a fence. And we would like to have a triangular fence, so we are choosing 3 of these places when we, how do we call it? Okay, these are the ends of my fence. And then in every possible coordinate, there's a cow. And we want to count the number exactly inside of this fence, so not at the edge of this fence. And if the number of cows is odd, then our fence is nice, or something like that. Okay, so if number of points is odd, then we are happy. So there are n over 3 possible fences here. We want to know how many of them are nice. Huh? the number of these points when we can put the answer. How? The size is infinite, but the coordinates are to 10 to the power of 9, maybe absolute value of the coordinates.
The number of fence posts.
That's a good question. Give me 1 minute. I think it's linear, but I will double check. Okay, it's not linear aligned. So it is 3,000. Oh, sorry, there's one more condition. So the fence is nice if the number of points is odd and area of the fence is integer. The area of the triangle that is generated by the fence has to be an integer. So it cannot be half something. Okay, there's one easier version of this problem. In the easier version, all of the coordinates of the points, of the posts, of the fence post are always even. So this is easier version. I will also give you this problem, like it is a problem from Code Forces, so I'll give you a link. You can take a look at the problem statement. But try to think about it, and then we'll talk about it tomorrow.
What's the output?
Yeah, what's the question?
What is the number of nice fences out of all possible fences? Awesome. Yeah, that's everything. Thank you very much.
Was not convinced. So, like, is there okay, so once you add a discover that this is you only update the range for that. Why do you update the range for this?